Our discussion will focus time domain representations of linear time invariant systems. We'll start off with the discrete time convolution sum. But first of all, let's look at an introduction to what we mean by time domain representations. Here we describe the relationship between the output of the signals for linear time invariant systems. Linear in the sense that if you double the input, you double the output, and you can decompose the input and then get the output as a decomposition of all the individual outputs due to each input. In time invariant, the system doesn't change with time. If I delay my input, I get a delayed output. This is also useful to predict and analyze linear time invariant system behavior. We'll start off with the impulse response, and then from there we can describe completely the behavior of any linear time invariant system. We should also note that any arbitrary input can be expressed as a weighted sum of time-shifted impulses, and I'll get into what we mean by that a little later. For linear time invariant systems, the output must be a weighted sum of time-shifted impulse responses. So here, for example, let's say I have a time sequence, an impulse sequence located at n equals 0. And our output consists of the impulse response. Now, if I delayed my impulse response, my corresponding impulse response will be delayed. That's what we mean by time invariance. And here, what we mean by linearity is where we can decompose any arbitrary input sequence into a sum of time-shifted impulses. Corresponding to our arbitrary input is our output sequence given by this equation, and I'll derive that in a later slide. And this sum is also called the discrete time convolution, or the convolution sum. So we'll see what we mean by an arbitrary input sequence as equivalent to a sum of weighted shifted impulses, and that can be easily shown with this example here, where we have a sequence of 3 numbers, which is equivalent to these sequence consisting of a single impulses, shown here, here, and here. Mathematically, x of n is decomposed into a sum of weighted shifted impulses, shown here. And for this example, since we have 3 numbers, we have 3 terms right here. Okay? One located at n equals 0, n equal 1, and n equal 2, weighted by x sub 0 for k equals 0, x1 for k equal 1, and x2 at k equal 2. And notice that's what we substitute appropriately in this equation for k equals 0, 1, and 2 at here and here. And we have the resulting equation shown here. Alternatively, this can be expressed with the values found in this sequence, where x sub 0 is 3, x1 is 2, and x2 equal to 1. So for k equals 0, we have this subsequence we'll call x0, consisting of a weight of x at k equals 0, where the impulse is located at n equals 0, or by this term here, which is the same as right here. And likewise for k equal 1, we have another subsequence of x1, which consists of a single impulse located at n equal 1, right here, and that's given by that term. And then for k equal 2, we have x2 located at impulse at 2. That's given by this expression here, which has a weight of 1. And we can take this overall sequence xn here and decompose it mathematically as follows: x sub 0, x sub 1, and x sub 2, shown here. So this is what we mean by an arbitrary input sequence consisting of a sum of weighted shifted impulses. Shifted and weighted impulses. Once again, let's work toward our convolution sum. Here we have a discrete time system described by our impulse response. So let's say we have an input, impulse located at there, and our corresponding output response is given as follows. Okay, so for a single impulse located with amplitude 1, area of 1 underneath this sequence, we have this sequence right here called the impulse response, denoted by Hn. Okay, now if I triple my input, increase my input by 3, okay, our output should also be correspondingly increased by 3. So where there's a 2 here, there's a 6, 1, and a 3, and a 3, and a 9. Likewise, if I shifted my impulse delayed by 1, I'm sorry, but double my input, then we have a shifted output right here, but it's also as doubled as well. So shifted by 1 and doubled. So that's what we mean by a time invariance. Now let's quickly look at the derivation of the convolution sum. Again, we start off with our arbitrary input shown here, and we have our impulse response due to a single impulse, and we want to see what our output is as a result of this. Well, we note earlier that we can decompose our sequence into a sum of impulses, time shifted weighted impulses, and our corresponding output is a result of this, okay, where x sub k and hn minus k. So our output can be described once we know the impulse response of the system, and it's given here as shown. Okay, so here we decompose this system, our input, as a sum of shifted weighted impulses, and we operate on this input with some operator h. It's some type of operation, could be some filtering operation, some type of linear operation that we perform on the this input sequence. And then we substitute xn for this expression here that was given here earlier. And we note that because of linearity, we can shift this operator inside this summation and put it around this impulse. But we know what this response is. It turns out to be hn minus k. So that's a result of this impulse that's shifted, and we get a corresponding impulse response that's shifted. Substituting this expression for this, we result in this following equation known as the convolution sum.